Hello, my name is Jack Callinan, and I'm working on low probability of detection signals. So the goal of the project was to create a 3-node CDMA network to try to demonstrate the effectiveness of avoiding a sophisticated adversary using degree of cyclostationarity and energy detection methods. So as you can see, the 3 nodes are two transmitters, 2 Alices, and a friendly receiver, Bob, listening in. And then the sophisticated adversary can be thought of as a enemy eavesdropper, Willie, over here. So to accomplish this, I used 4 different software-defined radios, SDRs, hooked up in via cables and using a GPS receiver to get a 10 megahertz and 1 PPS signal. So to maintain secrecy as well as allow multiple transmitters to communicate on the same frequency at the same time, I use something called CDMA, which is code division multiple access. The way it works is it takes orthogonal codes and multiplies them against every bit in the transmitted signal to allow them to transmit at the same time. The way orthogonal codes work is if they're multiplied together, they would add to 0. So if you multiply your signal by an orthogonal code, it allows you to transmit it and receive it while not getting any interference from the other signals being sent at the same time. Increasing the code length used by the codes allows me to increase the bandwidth that I'm using, which also aids in creating a more secret communication. But because the codes need to maintain orthogonality, I need to synchronize their transmission, because if they are even 1 second off from each other, they would no longer be orthogonal and would defeat the whole purpose of CDMA. So to synchronize the SDRs, the transmitter and receivers, I used a 10 megahertz signal coming from GPS as a reference signal to synchronize their clocks, and then a 1 PPS signal also coming from GPS to synchronize the transmission of the signal. On the left here is the synchronization before I added any of those features. So the delay between receiving and sending is not consistent, and so it's hard to account for. Whereas after I implemented those features, the delay was quite consistent and allowed me to account for it easily. So in terms of secrecy in this project, there are 2 different types, LPD and LPCD. LPD stands for low probability of detection, and that means low probability of detection for energy detection. So on the left, there are 2 different signals being transmitted there. The top one is 128 megahertz, and then the bottom one is 16 megahertz. If the 128 megahertz is sent, it can be buried in the noise because it has the same power as the 16 megahertz signal. So it has a lower peak power, meaning that it is easier to hide in the noise. Then there's LPCD, which is low probability of cyclic detection. That's the kind of aversion for degree of cyclostationarity, which is a type of detection that looks for the periodic nature of signals. So even if buried in the noise, a transmitted signal is going to have a periodic nature to it, which noise wouldn't have. And an enemy can look for that and then say that there's a signal being sent because of that. So on the top right here, this is like a periodic signal. It's getting repeated. And then at the bottom is something kind of like noise where there is no repetition. So the DCS would be low. So the results for my energy detection, if I used a sufficiently large bandwidth, the noise floor was high enough where that the signal I sent was hidden below it. And at no detection threshold could the enemy detect that there was a signal being sent. It's at a 50% detection probability, which is as effective as random guessing. On the top here is what it looks like if there is a signal being sent that has a lower bandwidth. And you can see that there are peaks. And those peaks are what the enemy looks for to decide if there's a signal being sent. And then the bottom is what it would look like if the signal is buried in the noise. And as you can tell, there's no way to tell if there's anything going on. Then the DCS detection results. If you use a low bandwidth, which can be achieved by having a low code length, you can see that there's a 50% chance of detection, which again is effectively like it's random guessing. But if you increase the bandwidth and code length, you end up getting a detection probability near 100%, which is obviously bad. That's perfect detection. I tried to implement DDC, which is a digital down converter, to speed up the process of DCS detection, but it resulted in some wonky results, which I have to further look into. But I want to continue doing this because this graph right here took about 2 minutes to create, whereas this one took about 2 hours to create. So I'd prefer to use DDC rather than just demodulating by hand. This is what my worst result from using the DDC was. And so that's obviously bad. As the code length increases, it seems to have worse detection, which should not be correct. So I'm going to look into that in the future. And then I'm also going to look into different ways to avoid DCS detection. On the right is a image from some of the reading I've been doing on how to avoid different DCS detection methods. Thank you. Are there any questions? Yeah, so if I increase the code length used in CDMA, because I'm multiplying it by every bit, the longer code length is gonna result in a larger bandwidth being used by the signal. And because of that, there will be an overall bandwidth increase, which can end up getting the signal buried in the noise while using the same amount of power as, say, a 16 megahertz signal. Thank you.